Okay, so at the end of the last video, I said that number 26 would require a different strategy. It really doesn't. It's, all of these are using limit as x approaches 0 of sine x over x. As soon as we see something that kind of looks like that, we're going to say we need to get this form isolated so that I can take advantage of the fact that that is 1. So sometimes the rewrite of the equation to get this by itself can be a little tricky. I think in number 25, it's particularly tricky. It requires creativity and insight to look at this and say, how can I get this sine x over x by itself following what I know about rational expressions? So for example, I know that in a rational expression, if I have a plus sign in the numerator or denominator, if I have a plus or minus sign in the numerator, I can split that fraction up. But if I have a plus or minus sign in the denominator, I can't. So I like plus signs in the numerator. They don't bother me at all. So I can say that equals limit as x approaches 0 of x over x plus sine x over x. So but all I've done is separate the fraction. Now, one thing we want to be careful in our notation as we're writing limits, this looks like it says limit as x approaches 0 of x over x plus sine x over x. So it looks like the sine x over x might not be part of the limit. So we want to be really clear using parentheses to show that those both terms are included in the limit. All right, now we're going to go back to the properties. I mentioned when we were back on page 61 that I was going to keep coming back to these properties of limits. This is one example of that. So one of the properties is this. If I have a sum of two functions and I take the limit, I can just add the limits. So a nice way to say that is the limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. The limit of a product is the product of the limits, and so on. All right, so these are properties that you can use. By the way, they are not trivial to prove. If you want, because for example, that's not true of sine, right? Sine of a plus b is not equal to sine of a plus sine of b. So how do we know that you can split the limit over the plus sign? So if you take a higher level calculus course, what you will do is come back to this definition in order to prove that. So you would only do that though in, after your Calc 1, Calc 2, Calc 3 differential equations, and you might eventually hit something called real analysis or advanced calculus, in which you would go back and prove those limits from the epsilon delta definitions. So a lot of you might not even ever do that class, but maybe a lot of you will. All right, anyway, what we get to conclude is that I can separate the sum into two different limits. So it's the limit as x approaches 0 of x over x plus the limit as x approaches 0 of sine x over x. So now I've succeeded in doing what I wanted, which is isolate that limit of sine x over x. But I still have to think about how I'm going to handle each of these things. So over here, I can reduce this is a rational expression now, so the rule is factor, simplify, substitute, right? But it's a little bit, because it's so simple, some of those steps sort of disappear. But I can simplify. And remember that x over x is only equal to 1 when x is not 0. If x were equal to 0, x over x would be undefined. For all other real numbers, for all non-zero real numbers, x over x is equal to 1, and we can simplify it. So remember, it's the fact that x approaches 0 actually bounds us away from 0 and says that while we're in this limit, the x cannot be equal to 0. It's anything else but 0. Therefore, I can reduce the limit and make it 1. All right, over here, I've limit as x approaches 0 sine x over x. That's the one we know, so we can just substitute that 1 anytime we want. All right, now, this is sort of an interesting one because I looked at the properties and I thought they should have a property about this, and they don't. And I didn't find it in the book. Maybe it's somewhere, but I didn't see this property listed anywhere. But there is a property that we could list separately, that the limit as x approaches 0 of k, where k is a real constant. All right, the limit as x approaches 0 of k, where k is a real constant, is k. All right, and I can sort of justify that with a quick graph, which is what would a graph of a constant look like? What does it look like, the graph of a constant? Like if I have y equals a constant, what does that graph look like? Yeah, it looks like a horizontal line. So that's the graph of y equals k. All right, so now no matter where my c is, as the x's approach c, the y values are going to approach k, which is also L, the limit. So the limit is k. All right, so that allows me to, I really need this property to say the limit as x approaches 0 of 1 is 1. So I'm dropping the limit. Like, you could argue that this is substitution. I'm substituting x equals 0 into the expression 1, and since there's no x, it just gives me 1. You could make that argument. I think this is a lot more direct way to say why the limit as x approaches 0 of 1 is 1. Anyway, so now I have 1 over here, and now calculus is as easy as 1 plus 1, which is 3. No, 2. 2. All right? So, but notice how I've clearly indicated every step. Like, it's not obvious that, like, if I have limit x approaches 0 of 1 plus 1, it's not obvious I can just jump to 2. All right? You need to say the limit as x approaches 0 of 1 is 1. You don't need to cite this property, but you at least need to show that I know there's a difference between 1 and the limit as x approaches 0 of 1, and I had to do something to get there. All right, so there you go. That's number 26. Next up, number 28, which is very tricky. We'll see that in the next video.